Let's see where the airplane actually goes over the ground. Although it is pointed to the north, it has been blown to the east by the wind. Recall that there are 4 steps to finding the resultant vector. In this case, we want to find the resultant velocity vector, which is the sum of the plane's velocity vector, or P, and the wind's velocity vector, or W. The first step is to find r sub x, or the x component of the resultant vector, which is the sum of the x component of the plane's velocity vector, or P sub x, and the wind's velocity vector,
W
or
sub x.
likewise r sub y is P sub y plus W sub y. To find r sub x, we note that the plane's velocity vector has 0 x component plus the x component of the wind velocity vector, which is 40 kilometers per hour. We get that r sub x, or the x component of the resultant velocity vector, is 40 kilometers per hour. R sub y is P sub y plus W sub y, where P sub y is the y component of the plane's velocity. That would be all 80 kilometers per hour, since the airplane is pointed due north. W sub y, or the y component of the wind's velocity vector, is 0. The wind velocity vector has no y component at all, since it is pointed due east. Therefore, r sub y, or the y component of the resultant velocity vector, is 80 kilometers per hour. From step 1, we have r sub x is 40 kilometers per hour, and r sub y is 80 kilometers per hour. The x component of the resultant vector comes from the wind is r sub x. The y component, which comes from the airplane's velocity vector, is r sub y. The resultant velocity vector, which is the actual path over the ground that the airplane takes, is the resultant vector r. Step 2 is to find the magnitude of the resultant velocity vector, which is the speed of the aircraft over the ground. We can write this as the absolute value or magnitude of the resultant vector. A less formal notation is to write the vector r without the arrow. This means magnitude. We have seen that the formula square root of the sum of the squares of the x component of the resultant vector is magnitude squared plus the y component magnitude squared. Substituting in 40 kilometers per hour and 80 kilometers per hour, squaring each and summing and taking the square root, we get that the speed of the aircraft over the ground is 89.44 kilometers per hour. This is a 2 significant figure problem. Therefore, we must round our result to 2 significant figures. We report that the speed of the aircraft over the ground is 89 kilometers per hour. Its indicated airspeed is 80 kilometers per hour, but it is actually doing 89 kilometers per hour over the ground. Step 3, find the reference angle theta ref, which is the angle whose tangent is, or tangent minus 1, magnitude of the y component of the resultant vector divided by the magnitude of the x component of the resultant vector. Looking at the picture, we see that the reference angle, recalling that the reference angle is the angle between the vector and the x-axis, not the y-axis, not this angle here. The reference angle is this angle. It is the angle whose tangent is the y component over the x component. We substitute in for the y component 80 kilometers per hour, for the x component 40 kilometers per hour. We get that the reference angle is 63.43 degrees, or 63 degrees to 2 significant figures. The final step, step 4, is find theta in standard position. But this is a first quadrant angle. For first quadrant angles, the reference angle is theta itself. Theta is 63 degrees. The actual velocity vector of the aircraft over the ground is a magnitude or a speed of 89 kilometers per hour at an angle of 63 degrees in standard position, or we could say 63 degrees north of east.